Okay, well, welcome back to our course on system engineering. We're continuing to make some good progress as we go through some of the critical areas in this textbook. And so we're continuing to go through these basic important concepts in system engineering. We've talked about software processes, agile development, requirements engineering, system modeling, architectural design, design and implementation. So various aspects of how you go about formulating what you want to be doing with your software. And today we're going to be getting into software testing. And so for software testing, the things that we'll be having for topics is we'll talk about development test, test-driven development, release testing, and user testing. And so each of them has a separate purpose and focus. So for program testing, it's intended to show that a program does what is intended to do and to discover program defects before it is put into use. That's always a good thing. When you test software, you execute a program using artificial data. And so you come up with a test data set that is trying to validate it, that can work as it processes that information. You want to check the results of the test for errors, anomalies, or information about the program's non-functional attributes. And you can reveal the presence of errors, but not their absence. So you find errors, and so let's just focus on that part. And testing is a part of a more general verification and validation V&V process, which also includes the static validation techniques. So what are the program test goals? You want to demonstrate to the developers and the customer that the software meets its requirements. So for the customer software, this means that there should be at least one test for every requirement in the requirement document. For generic software products, it means that there should be tests for all the system features plus combinations of these features that will be incorporated in the product release. So you're trying to mimic what the customer would be doing in generic software development. So to discover situations in which the behavior of the software is incorrect, undesirable, or does not conform to its specification, those are things you want to uncover. So defect testing is concerned with rooting out undesirable system behavior, such as the system crashes, unwanted interactions with other systems, incorrect computations, and data corruption. In terms of validation and defect testing, the first goal leads to validating the testing. You expect the system to perform correctly using a given set of test cases that reflect the system's expected use. Then the second goal leads to defect testing, that the test cases are designed to expose defects. The test cases in defect testing can be deliberately obscure and need not reflect how the system is normally used. So what are the testing process goals? You have validation testing. So you want to determine to the developer and the system customer that the software meets its requirements. A successful test shows that the system operates as intended. For defect testing, you want to discover faults or defects in the software where its behavior is incorrect or does not conform with the specification. A successful test is a test that makes a system perform incorrectly, so exposes a defect in the system. So here is an input-output model of program testing. And so you have the input causing anomalous behavior. So you have the input test that goes into the system, and then you have outputs which reveal the presence of defects. So this is what you're trying to find. You're trying to go to the system and engage in a variety of different ways. And eventually you want to get to a point that there's no defects, there's no errors that come out. So why don't we consider these two things, verification versus validation? Verification means we are building the product right. The software should conform to its specification but for validation, we are building the product right. The software should do what the user really requires. And so this verification and validation confidence, the aim of verification and validation is to establish confidence that the system is fit for purpose. It depends on system's purpose user expectations and marketing environment, the software purpose, the level of confidence depends on how critical the software is to the organization. For user expectations, users may have low expectation of certain kinds of software. And for the marketing environment, getting your product to market early may be more important than finding defects in the program. What about inspection and testing? Software inspection is concerned with the analysis of the static system representation to discover problems, which is static verification. There may be a supplement by tool-based documents and code analysis, which is discussed in more detail in chapter 15. And software testing is concerned with exercising and observing product behavior, dynamic verification. So the system is executed with test data and its operational behavior is observed. So here is inspections and testing, just to give you an idea. So inspections, you can be looking at all these different things, looking at the requirement specs, software architecture, the UML models, the data schemas in the program. So that's one way that you can do assessment of the system. And then you can be doing testing. You can be having a system prototype and you test the program against what that system is supposed to be accomplishing. You can have prototypes and eventually have the system for record that you want to be delivering. So for software inspections, these involve people examining the source representation with the aim of discovering anomalies and defects. Inspections are do not require execution of a system, so there may be used before implementation. There may be applied to any representation of the system, requirements, design, configuration, data, test data, etc. They have been shown to be effective techniques for discovering program errors. So what are the advantages of inspection? During test, errors may mask, that is hide other errors. Because inspection is a static process, you don't have to be concerned with interactions between errors. Incomplete versions of a system can be expected without additional cost. If the program is incomplete, then you need to develop specialized test harnesses to test the parts that are available. As well as searching for program defects, and inspection can also consider broader quality attributes of a program, such as compliance with standards, portability, and maintainability. For inspections and testing, inspections and testing are complementary and not opposing verification techniques. Both should be used during verification and validation processes. Inspections can check conformance with a specification, but not with conformance with the customer's real requirements. Inspections cannot check non-functional characteristics such as performance, usability, etc. So here's a model of the software testing process. And so you have test cases, you have test data, test results, and finally you have a test report. And so you want to design the test case with the test data, prepare the test data, and then iterate that. Then you run the program with the test data that you've assembled. You get the results, compare the test to the test case, and see if this makes sense, that the results that according to what your predictions would hold, that what you should be getting. In terms of stages of testing, you have developmental testing, release testing, and user testing. So for development testing, this is where the system is tested during development to discover bugs and defects. For release testing, this is where a separate testing team tests a complete version of the system before it is released to users. And finally, for user testing, this is where users or potential users of a system test the system in their own environment. Okay, let's focus on development testing. Development testing includes all testing activities that are carried out by the team developing the system. And so there's unit testing, component testing, and system testing. For unit testing, this is where individual program units or object classes are tested. Unit testing should focus on testing the functionality of objects or methods. Component testing is where several individual units are integrated to create composite components. Component testing should focus on testing components interfaces. For system testing, this is where some or all the components and the systems are integrated and the system is tested as a whole. System testing should focus on testing component interactions. For unit testing is the process of testing individual components in isolation. It is a defect testing process. Units may be individual functions or methods within an object classes with several attributes and methods, or composite components with defined interfaces used to access their functionality. For object class testing, you would have a complete test coverage of the class involved. So you would be testing all operations associated with an object. You would be testing and interrogating all object attributes and exercising the objects in all possible states. Inheritance makes it more difficult to test object class test, as the information to be tested is not localized. So that's something that with your UML models and other types of information, you could get a better sense of what needs to be tested to be thorough. So here's an example for the weather station object interface. And so you have a variety of different things that you're going to have to be exercising: reporting weather status, going into power save, turning on remote control, and then having a command to what you would want to do, reconfigure, start, and shut down. So they're also the type of things that you would be doing. So for the weather station testing, you need to define test cases for weather report, calibrate, test, startup, and shutdown. Using a state model, identify a sequence of state transitions to be tested and the event sequence to cause these transitions. For example, you can go from shutdown, running, to shutdown. You can go from configuring, running, testing, transmitting, and running. And so you can see these various ways: running, collecting, back to running, summarizing, transmitting, and running. So the ability to go from state to state. Automated testing is also very useful. This is whenever possible. Unit testing should be automated so the tests are run and checks without manual intervention. Another advantage of this is, since it's automated, you know that it's always going to be done the same. So you can make use of an automated framework to write and run your program test, and unit testing frameworks provide generic test classes that you extend to create specific test cases. They can then run all of the tests that you have implemented in a report, often through some GUI, on the success of otherwise of the test. For automated test components, a test part where you initialize the system with the test case, namely the inputs and expected outputs. A call part where you call the objects or methods to be tested, and an assertion part where you compare the results of the call with the expected results. If the assertion value is true, the test has been successful. If false, then it has failed. So for choosing the unit test cases, the test cases should show that when used as expected, the components that you are testing does what it's supposed to do. If there are defects in the components, these should be revealed by test cases. This leads to two types of unit test cases. First is that they should reflect normal operation of a program, and it should show that the components work as expected. And number two, the second part is the kind of test case should be based on testing experience where common problems arise. It should use abnormal inputs to check that these are properly processed and do not crash the component. For testing strategies, you can have partition testing, or you can have guideline-based testing. So partition testing is where you identify groups of inputs that have common characteristics and should be processed in the same way. You should choose this testing from within each of these groups. And then for guideline-based testing, this is where you use testing guidelines to choose test cases. These guidelines reflect previous experience of the kinds of errors that programmers often make when developing components. So for partition testing, the input data and the output results often fall into different classes where all members of the class are related. Each of these classes is an equivalence partition or domain where the program behaves in an equivalent way for each class member. Test cases should be chosen from each partition. So here's an illustration of an equivalence partition. And so you can have variety of inputs, and so you're going to be selecting the input equivalent partitions, fold those into the system, and then you're validating that you're getting the correct outputs. So here's another illustration of equivalence partitions. And so you can be seeing here are various numbers between various ranges. And so these could be examples of the type of inputs that you want to verify, and especially checking at the boundary conditions where you're binning data, informatics, whatever, into different groups. So for testing guidelines or sequences, the test software with sequences which have only a single value. So you want to be doing that kind of test. You want to use sequences of different sizes and different tests, and you want to derive tests that are the first, middle, and last elements of a sequence are accessed, and tests where a sequence of zero length. And so these would be things where you potentially could be getting errors. So for general testing guidelines, you want to choose inputs that force the system to generate all error messages. You want to design inputs that cause input buffers to overflow and repeat the same input or series of inputs numerous times. You want to force invalid outputs to be generated and force computational results to be too large or too small. For component testing, the software components are often composite components that are made up of several interacting objects. For example, in the weather station system, the reconfiguration components include objects that deal with each aspect of the reconfiguration. You access the functionality of these objects through the defined component interface. Testing composite components should therefore focus on showing that the component interfaces behaves according to its specification. You can assume that unit tests on the individual objects within the components have been completed. For interface testing, objects are to detect faults due to interface errors or invalid assumptions about interfaces. And the interface types are parameter interfaces, shared memory interfaces, procedural interfaces, and message passing interfaces. So for parameter interfaces, the data is passed from one method or procedure to another. For shared memory interfaces, the blocks of memory are shared between procedures or functions. And for procedural interfaces, subsystems encapsulates a set of procedures to be called by another subsystem. Finally, message passing interfaces, subsystems request services from other subsystems. So here's the kind of things that visually gives you an idea that a test case is going to be looking at these various interfaces and how they engage with the system. And then you can be looking at how the functionality goes forward. For interface errors, the couple things we'll want to mention is as interface misuse. A calling component calls another component and makes an error in its use of its interface. That is, the parameters in the wrong order. Interface misunderstanding, a calling component embeds assumptions about the behavior of the called component, which are incorrect. And finally, timing errors. The calling and the calling component operate at different speeds, and out-of-date information is accessed. For interface testing guidelines, you want to design tests so that the parameters to a called procedure are in the extreme ends of the ranges. You always want to test pointer parameters with null pointers. You want to design tests which cause the components to fail. You want to use stress testing in message passing systems, and in shared memory systems, vary the order in which components are activated. For system testing during development involves the integrating components to create a version of the system and then testing the integrated system. The focus in system testing is testing the interactions between components. System testing checks that components are compatible, interact correctly, and transfer the right data at the right time across their interfaces. System testing tests the emergent behavior of a system. For system and component testing, during system testing, reusable components that have been separately developed and off-the-shelf systems may be integrated with newly developed components. The complete system is then tested. Components developed by different team members or sub-teams may be integrated at this stage. System testing is a collective rather than an individual process. In some companies, system testings may involve a separate testing team with no involvement from designers and programmers. And for use case testing, the use cases developed to identify system interactions can be used as a basis for system testing. Each use case usually involves separate system components, so testing the use case forces these interactions to occur. The sequence diagrams associated with the use case documents the components and the interactions that are being tested. So here is a diagram showing the collecting weather data sequence chart. And so we have the information system, and we've walked through these type of interactions before. So you have the SATCOM, the weather station, the comlink, and the weather data. And basically it trickles down to where you're getting the weather data, and the results of that are then passed back to the information system. So you get a request, it trickles through, comes back, and that data is successfully passed on. So for test cases derived from sequence diagrams, an input of a request for a report should have an associated acknowledgement. A report should ultimately be returned from the request. You should create summarized data that can be used to check that the report is correctly organized. An input request from a report to weather station results in a summarized report being generated. Can be tested by creating raw data corresponding to the summary that you have prepared for the test of SATCOMs, and checking that the weather station object correctly produces a summary. This raw data is also used to test the weather data object. For testing policies, exhaustive system testing is impossible, so testing policies which define the required system test coverage may be developed. Examples of testing policies is all system functions that are accessed through menus should be tested. Combinations of functions, for example, text formatting that are accessed through the same menu must be tested, and where user input is provided, all functions must be tested with both correct and incorrect input. What about test-driven development? So test-driven development is an approach to program development in which you interleave testing and code development. Tests are written before code, and passing the test is the critical driver of the development. You don't code incrementally along with the test that you for that increment. You don't move on to the next increment until the code that you have developed passes its tests. And so test-driven development was introduced as part of agile methods such as extreme programming. However, it can be used in plan-driven development processes as well. And so here's an illustration of test-driven development. You identify new functionality to write the test, run the test, and verify that it passes. And then if it is, you're fine. If not, you implement functionality and refactoring, and you rerun the test until you've completed that cycle. So for test-driven development, with the process activities, you start by identifying the increment of functionality that is required. This should normally be small and implementable in a few lines of code. You write a test for this functionality and implement this as an automated test. You run the test along with all other tests that have been implemented. Initially, you have not implemented the functionality, so the new test will fail. You implement the functionality and retest it, rerun the test, and once all tests are successfully run, you move on to implementing the next chunk of functionality. So what are the benefits of test-driven development? So for code coverage, every code segment that you write has at least one associated test. So all code written has at least one test. For regression testing, a regression test suite is developed incrementally as a program is developed. For simplified debugging, when a test fails, it should be obvious where the program lies. A newly written code needs to be checked and modified. And for system documentation, the tests themselves are a form of documentation that describes what the code should be doing. So you can be leveraging these different ways to ensure that you get your proper documentation at the end. For regression testing, this is testing the system to check that the changes have not broken previously working code. In a manual testing process, regression testing is expensive, but with automated testing, it is simple and straightforward. All tests are rerun every time a test is made to the program. Test must be successful before the change is committed. What about release testing? So release testing is a process of testing a particular release of a system that is intended for use outside of the development team environment. The primary goal of the release testing process is to convince the supplier that of the system that it is good enough for use. So release testing therefore has to show that the system delivers its specific functionality, performance, and dependability, and that it does not fail during normal use. Release testing is usually a black box testing process where tests are only derived from the system specification. In terms of the release testing and system testing, the release testing is a form of system testing. There are a couple of important differences, though. A separate test that has not been involved in the system development should be responsible for release testing. System testing by the development team should focus on discovering bugs in the system, that is defect testing. The object of release testing is to check that the system meets its requirements and is good enough for external use, that is validation testing. For requirements-based testing involves examining each requirement and developing a test or tests for it. For the Medcare system requirements, if a patient is known to be allergic to a particular medication, the prescription of that medication shall result in a warning message being issued to the system user. If a prescriber chooses to ignore any allergy warnings, they shall provide a reason why this has been ignored. There might be some possible exceptions or some mitigations. For requirements testing, you set up a patient record with no known allergies. You prescribe the medication for allergies that are known to exist. You check the warning message is not issued by the system. So for setting up a patient record with known allergies, then you'd have to check that. Set up a patient record with allergies or 2 or more drugs are recorded, and prescribe 2 drugs that a patient is allergic to, and prescribe the drug warning and overrule the warning. So here are the various things, the scenarios that you can be doing in terms of requirements testing to make sure that the system operates properly for each of these. So I won't read this, but here is a use case scenario for the Medcare system. And so you have George, a nurse who specializes in mental care. One day for a home visit, George logs into the system to print out a schedule. He's prompted for his key phrases to encrypt on his laptop. One of the patients that he visits is Jim, and so he's trying to help him with that. And so we're just seeing this scenario. And so after finishing his consultation, George returns to the clinic, upload his results, and the system generates a call list for George and those patients who he has to contact for follow-up information. So you can see how it's been working out and working for a specific patient and the things that he helps us with diagnosis. So for features tested by a scenario, you want to have authentication, logging into the system. You have downloading and uploading of specific patient records onto a laptop for use. You can have home visit scheduling, encryption and decryption of patient records on a mobile device. You always want to maintain protection of personal identifiable information. You want to have record retrieval and modification as necessary, and links with the drug database that maintains side effect information. And finally, the system for call prompting. For performance testing, this is part of the release testing that may involve testing the emergent properties of a system, such as performance and reliability. Test should reflect the profile of use of the system. The performance test usually involves planning a series of tests where the load is steadily increased during the system performance until the system performance becomes unacceptable. Stress testing is a form of performance testing where the system is deliberately overloaded to test its failure behavior. For user testing, users or customer testing is a stage in the testing process in which users or customers provide input and advice on system testing. User testing is essential, and even when comprehensive system and release testing have been carried out. The reason for this is that influences from the user's working environment have a major effect on the reliability, performance, usability, and robustness of the system. These cannot be replicated in a testing environment. In terms of types of user testing, there's alpha testing, there's beta testing, and there's acceptance testing. So alpha testing is sort of the first time you work on this, and the user of the system work with the developer team to test the software at the developer site. Beta testing is a release of the software is made available to the users without allow them to experience the system and raise problems that they discover and tell them to the system developers. And finally, acceptance testings is when customers test the system to decide whether or not it's ready to be accepted from the system developers and deployed to the customer environment. Primarily, this is for customer systems. And so here is an illustration of the acceptance test process. You define the criteria, you plan for the acceptance testings, you derive an acceptance test, you run the test, you negotiate the test result to see if it meets it, and then you accept or reject the system as a result of what you've gotten. So here's a listing of the stages in the acceptance test process. You define the acceptance test, you plan the acceptance test, you derive acceptance test, run acceptance, negotiate test results, and reject or accept the system. And that's what we were just showing in this figure here. And you can see how it's a linear process. You have to do one before you can go to the next one. So in terms of agile methods and acceptance testings, in agile methods, the user customer is part of the development team and is responsible for making decisions on the acceptability of the system. Tests are defined by the user customer and are integrated in with other tests, and that they are run automatically when changes are made. There's no acceptance test process. The main problem here is whether or not the embedded system is, quote, typical and can represent the interests of all system stakeholders. Okay, just a couple slides for key points. Testing can only show the presence of errors in the program. It cannot demonstrate there are no remaining faults. That's an important thing to keep in mind. Development testing is the responsibility of the software development team. A separate team should be responsible for testing the system before it is released to customers. Development testing includes unit testing, in which you test individual objects and methods. Component testing is where you test related groups of objects, and system testing is where you test partial or complete systems. When testing software, you should try to break the software by using experiences and guidelines to choose types of test cases that have been effective in discovering defects in other systems. Wherever possible, you should write automated testing. The tests are embedded in a program that can be run every time a change is made to the system. And so you constantly go back to a gold standard in testing. Test first development is an approach to development where tests are written before the code is to be tested. Scenario testing involves inventing a typical usage scenario and using this to derive test cases. And finally, acceptance testing is a user testing process where the aim is to decide if the software is good enough to be deployed and used in its operational environment. Okay, well, that's it for this lecture. Thank you very much.